Good morning. Sounds like you're all awake this Friday morning. Hopefully you enjoyed the nice weather this morning. Not so much rain as we have usually, lately at least. Now, at some point today, I would like to just catch up on the exercises last week. Did everything work out as you wanted it to, or did you have something that you kind of stumbled upon and didn't get back up again? We'll take it from there if there's something, but this is also a good time if there's something you say, well, we should probably kind of discuss this all together. There's usually a question regarding one of the exercises regarding why did the solution use a log transform for the wind speed, for instance. It's fine to do either or. That's just a choice. The log transformation of the wind speeds has one added value, and I don't know if you've thought of what that is. When you do the log transformation of some numbers and then do some modeling and then you do some prediction and then you transform back.
It ensures that the end result is positive. Wind speeds.
Exactly, so the wind speed will always be positive. Whereas if you do what some of you probably did, well, you will end up having negative wind speeds. And depending on how you define direction, it's okay, but often it's not associated with speed to be negative. But those are things where you kind of have to make sure that you understand how things are phrased. Today, we will continue our, I would say, applied use of regression methods, focusing on global trend models. Then there'll be time for some examples, and in between, we will discuss how to do assignments. Because the first one is going to be available today, but not just yet. So basically, what you also did, one of the assignments last week, was to use as a function of time as the independent variable. Rather than using something you measured, you just say that you have the observation numbers, and then you want to say, well, how can I model what is happening over time? And that is basically the main topic for today. And to some extent, the rest of the course, just in many different ways. There we will be using time as our kind of stepping from one point to the next. And then there may be one or more observations, but we won't, well, we will also allow that you observe some predictors, as you had in the small case last week, but mostly we will focus on how do we predict forward in time. So, one way of formulating this is the following. You have the observation. Now, yn is the last, so we have uppercase N observations in total, plus j, where j may be positive or negative. Then you can get to any observation, both previous observations by having it negative, current by 0, and future by positive. And then we have some function of the time shift multiplied on our parameters, and then we have, of course, the noise element that is associated with the corresponding observation. The trick is this f of j. Now, we want to do things in a linear way, and if we take a model like the top one there, y equals phi 0 plus phi 1 t plus epsilon t. Then, well, we could easily write it like this. The difference here is, well, we want to, this is stated with t here rather than n plus j. That's the main difference. So, what we want to say is, well, we want to make predictions out in the future, given observation up to the current time. We can do it like that. Now, I don't know how many of you have done a lot of different regression models, but if we go back to how things were last week, what is it that we have up there? If we look at the observations, have the model yt equals phi 0 plus phi 1 t plus epsilon t. Now, how would we, given a number of observations of this kind, given what we did last week, how would we solve to find the parameters? Yes, so we want to get to the normal equation. Before we get to that, we kind of have to define our structure. So we have some observations, y1 through yn. And then we have the so-called design matrix. And then we have the parameter vector, that in this case is phi 0 and phi 1. And then we have the corresponding errors over here, epsilon 1 through epsilon n. So what goes in here? Yes?
What is on the first column and then the values in the next, like 1 to n?
Yes, so a column of ones, and then the second column, you have the numbers from 1 through n. Indeed. Now, what happens in reality is that if you have something that is running in continuous time, I can tell you the data that you get for the first assignment are measurements of ambient temperature. I took them from my house just because I logged them anyhow. I record them every minute, but you only get every 30th measurement, because otherwise the calculation time is probably going to grow too high. But that is to say, I got some 20,000 observations. Of course, now 20,000 is not a huge number nowadays, but I don't know how many of you have experienced numerical errors in practice. Anyone? Did the introduction to numerical algorithms and learned what not to do when doing matrix operations, stuff like that? So look at this column. I'll get back to it later, I think, where it's easier to see what is actually going to happen. So what Gandalf said is basically we just have to solve the normal equation, and if we define this here as our current x, and now I'll just use a phi with no subscript to define the parameters there. Do you recall what the solution is? I know some of you know it. Some of you spend a lot of time doing it, so I want someone else to say it. Because this is something I want you all, I promise I won't get around and wake you up at 2 o'clock in the morning. That's something I just want you to know, because you will see it so many times, not just here, but many places. And if you don't understand what is going on there, then there's a lot of things that you don't understand. So that's why I will ask this question too many times, probably, but I will. So how do I get an estimate of phi? Yes?
X transpose times X divided inverted.
Sorry? Inverted, yes.
Times X transpose
And then X transpose,
Y.
and the column Y, exactly. Now, that is what we want to do. Now, what happens when you're going to do predictions as given there? The order of magnitude of this number here, n plus j, that is going to grow, right? When we get 10 times more observations, the number is going to be 10 times higher. When you get 1,000 observations more, or 1,000 times more, all of a sudden, the precision of these numbers is multiplied by a large number on one of them, and not so much on the other. And that's where you may run into numerical problems. You also get into it here in X transpose X. It's not so bad with what we're going to do today, but what we're going to do next week. And maybe we'll peep into it today as well. The problem is, when you do X transpose X, what do you get? You get the inner product in the diagonal. You get the inner product of this one column with itself. That's just the sum of the number of elements. That's doable. But then you also get the inner product of this over here. Here you have n squared. So when n is becoming large, n squared is going to be very large, right? All of a sudden you have matrices, say if n is 1,000, that's not a large number. Then it's 1,000,000, and then you have a 1. Then you have, say, a sum of 1,000 in the other element. And you want to invert this. The order of magnitude between the elements in that matrix is going to be larger and larger and larger as n is increasing, which means that you will at some point run into numerical precision problems. Of course, not if you do everything analytically by hand, but I don't expect you to do that. So, and if you're good at it, of course, but that's an assumption. The problem is that the time is corresponding to the beginning of time. What we propose here is to shift time so that time is relative to now. Now is the most recent observation. That means that when we want to make predictions in this way, just write the bottom to have it underneath here. N plus j equals, this is this, I won't write it like that. I would rather write it over here to have the contrast. Then we have yt. Let me write it the same way to make it to not. It is written as t there, and then equals, and then I'll use theta rather than phi as parameters, but the structure is still a linear regression model where I have time minus n. So effectively it's the same regression model. If you look at the parameters in this model and in this model, what I will just do is to write the design matrix for this model. You get a column of ones again. Then down here, y1, y2 down to yn. When t is n, then you have a n minus n, so that's a 0 down here. Let's just have n minus 1 here. N minus 1 minus n, that gives us minus 1. And then we go backward. What do you get when t is 1? Well, you get 1 minus n, or I would write it as minus n minus 1. That is, of course, the same. But I want it this way because then they are all having a negative sign in front. So basically what you do is you start with a 0 and then you just count downwards. Now, from the numerical perspective, you can say this is equivalent to this one over here. The difference is when you want to do the predictions, when you do the X transpose X, you get the same numerical challenges. Not when we go to do, this is when you do global models. When you have tons and tons of observations, you don't want to do global models, you want to do local models, which is the theme for next week. So, but when you're doing predictions, if it's just a short term, j will be a small number, which means that it'll be easy to do that. Now, what is then the relation between the thetas and the phis? Yes?
Theta 0 is in the first model the actual value of y at time 0.
Theta 0 is the value of
The estimated value, no, the mean value of y.
at time
0.
no. Not at time 0. I can say the latter one is the easy one. So what we say here, theta 0 is representing the intercept. And what we do is that if you have some data and you made a linear regression model, let's just say n is the current time there, and this here is time 0, then this here is phi 0, right? That one there is theta 0 exactly. So what is the relationship? And then if this is 1, it becomes a little bit small, then this is phi 1. Likewise, n plus 1, theta 1, right? Now I almost answered the second bit here, which is the easy part. The slope, if it's the same model, is the same slope. So this is phi 1. Now, theta 0 is not what y was at time 0 here, but at time n. So basically you can say that's taking the first model up there and say you have your phi 0, which is the initial offset, and then you have phi 1 times n. And that's the part I didn't hear you saying.
Yeah, I just mixed up.
I think what you do is exactly as you, what is likely to happen is that you mix up the zeros, as you say, because
The symbols.
symbols. Ah, okay, sorry. So for the other implementation, this is 0, and this here is minus n minus n minus 1, and so forth. And we will use this notation for the trend models, because that everything, all the estimates that you get, this estimate here of the intercept is exactly the predicted value at the current time, right? So you have your predictions, you have your slope, everything is just in your estimate. You don't have to do any calculations to do that, because what you have here, the expectation of yn plus j, well, j if that is 0, given n, is exactly just theta 0. So basically it's just a shift of time. We do it also because we can make some nice algorithms that makes life easy. So for this model here, if we're going to use the framework defined like this, basically what we did, how we did define this was having rows over there, one, and now I just write it as j on theta plus epsilon n plus j, because if j is 0, we see it from up there. Well, then we have a 1, 0 row here. And if j is -1, well, you get a -1. So that's the function that we implicitly used for f of j. Now, when you go one step forward, basically what you do is, well, you just increase j by 1. That's fairly easy in this kind of model. Linear models, simple linear regression models, are always nice and easy to work with. And we have, you can say, equivalent to what we had. Here we just have it +1. So that's the easy part. Now, the more tricky part of this is to say, how do you get from 1j to 1j plus 1? How do you step forward in time if you want to do it with a matrix operations rather than having to reapply the function? Because what I want to do is to get to a point where everything are constant. When I update, I don't have to keep track so much of what n is. To some extent, I need to keep track of it, but at some point, you actually can forget how far you got in the sequence, and you just progress. So what you want is the first coordinate here should be the same, so you want a 1, 0, and the second one should be the sum of those two, 1, 1. We define this matrix as L. It's a forward shift operator. So when you pre-multiply by L, you go forward in time. If you pre-multiply by the inverse of L, can you guess what happens? Multiplying by L is forward, inverse goes backwards. So this is the transition. Any model that you can make as a linear trend model, could also be quadratic or polynomial or whatever, you should have a matrix like this that can shift you forward in time. Otherwise, you're not in this particular family of models. So in general, what you have, well, we have the same definition up here. N plus j, yn plus j is equal the transpose of some function of j times the parameter vector plus epsilon. And it's a requirement that you can get to f of j plus 1 by pre-multiplying by a transition matrix on the fj. We can specify an initial value, and by specifying the initial value and L, you can get to any fj without actually doing anything else. You just have to apply L a sufficient number of times. So some examples. Well, we have looked at the linear trend model. An even simpler model is the so-called constant mean model, where you basically just estimate what is the mean value. Every time you get a new observation, you update the estimate of the mean value. I don't know if any of you have done that in another setting before, but how do you estimate a mean value? What do you do? If you just don't look at the slides, how do you estimate the mean of a number of observations? Yes? You calculate the average by doing calculation-wise. What do you do? Exactly. You sum up all the observations and divide by the number. Now, written as a linear regression model, maybe you're kind of finding big bullets for small birds, but basically what you do, we're looking at solving the normal equation. If your model is just a constant mean model, all you have is a column of ones. So x transpose x is the inner product of a column of ones. That is just n, right? So what it says here is 1 divided by n. And the inner product of a column of ones with the y's, that's the sum of all the observations. So we are indeed making the sum of all of the observations and divided by the number of them. Just so, it's a little bit more complicated way of just doing a sum, but it will be nice to just have the analogy at some point. You can also do a quadratic model. You can do it in any polynomial order. The reasons for not just having j squared here, but j squared half, that is kind of associated with a Taylor expansion, and it means that the coefficients in the L matrix are nicer. So of course you can do other formulations of it, but it's just nicer to have it on this form. Then you can do it. So those are, you can say it's trivial to go to a higher and higher order when you figured out the pattern. What I think is more interested in is the harmonic model, so you can have a signal with some period, and then you can say a sine or a cosine of that. I don't know how many of you played around with signals and trying to do Fourier transformation, stuff like that. Anyone? So what is the added value of having both a sine and a cosine? What does it represent? Yes? Exactly. So it gives you you say, where are you in the signal, and you can adjust the phase by shifting where you are. And that's the important part. So what happens here is, if you look at it, sine of 2 pi over p, which is the period, this part here, then you just evaluate it with j. What happens when you go forward, when you increase j by 1? What is actually happening? You have the easy way to represent it is by a rotating system, right? So you have how far have you rotated, and then by having a set both sine and cosine, you can say what is the reference phase. When you step forward, one step forward in time, it corresponds to a certain rotation, and the next one, and the next one, and the next one, they're all equal, because you're rotating at a constant angular velocity. So you can do this where what you do, the L matrix here is basically just a fixed rotation a number of degrees of your system. Thereby, even though the formula here has a nonlinear dependence on j, when you formulate it by L, an initial value, you just have a matrix of coefficients that you multiply on. It's a little bit mind-boggling at first, but I think you've all done the linear algebra, and you can do a rotation of a matrix, right? Rotation of a coordinate system. That's all that happens repeatedly. Do you remember you've done it? I'm certain you have. I hope you remember. But that's just to say that the family of models is not just, you can say, the typical regression models, but you can do other things that are more complex. And of course, you can do any combination of these if that makes you happy. So We pretty much did this. If we have the model up to time n, then we kind of collect all the f values here as rows, and we have theta n. Now, from now on, theta will have subscript n to represent this is the estimate after having n observations. Because when I get the next observation, I'll get a new estimate. Typically, we say that now we're done measuring, but what we're doing here is that we'll continue measuring. We get new observations, and new, and of course, whenever we get a new observation, we want to update our estimate. So, when we look at what we have up here, and we effectively want to do this, we solve it the same way, then we should just look a little bit at what do we have. Well, we have this estimator. So xn here is this design matrix with n rows. When it has n rows, the largest number related to n is n minus 1, because we start with index 0 down here. So we have a small indexing there we have to keep track of. Now, that is fairly easy. I will write it as Fn inverse h. Basically, let me just write it up here as well. So I have my theta hat is equal to, we call this xn, xn transpose, xn inverse, xn, and I should write n there as well. Here's transpose, and then y, and I don't think I won't give it a subscript n, but it's implicit that this is the vector of elements up to time n. So that's the estimator. I will define it as Fn inverse, so that's basically saying that x transpose x, that's my f, and then hn, which is then xn y. Just like this. And what I want you to look at, when you do this matrix multiplication up here, normally, I don't know when you last did this by hand. I usually don't, but I will give it a try right now. If you have a matrix that you want to multiply, let me have the first, write it like it is up there. Then the way I was taught to do this, I have this matrix. I want to multiply this with the transpose of that, so I will write it out here as the transpose. So then I get a column, a row of ones, and then I get the row down here, start with minus n minus 1, parenthesis, dot, 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 and then I have a 1 and a 0. Sorry? Minus 1, thank you. I knew exactly where you wanted that minus. So, at least this was how I was taught to do it. And it's good in order to see what do I actually get for the result down here. The typical way you do it is that you say, well, then this element is just the inner product with this column and that row. So all these elements are just the corresponding inner product, right? That's what you've done. Now, you can do it in a different way as well. I could say, well, what I do is rather than finishing one element at a time, what I do is I take the 1, 0 here and the 1, 0 here and say, well, that gives me a full matrix. So that gives me a 1, 0, 0, 0 matrix plus, and then I do for the next one, well, I get a 1, 1 here, then I get a minus 1 here, and a minus 1 there, and down here I get again a 1. And if I take the next one here, here I have a 1, and there I have a 1, so that is plus 1. Here, well, that next one there is a minus 2, right? So I say that becomes a minus 2 and a minus 2. And this down here is minus 2 times minus 2. So that is 2 square. And then I'll just say plus. Oh, and here'll be minus. Like that. So rather than doing it, finishing one element at a time, you can take one layer, so to speak, at a time. And that's the motivation for writing it like this. So you finish the inner product of the corresponding f's with itself, and then you sum over the various values of j. That was fn. Hn, well, it's just about the same story. You just only have 2 elements you get out instead of 4 in that particular case. Because j is only 1 by n dimensional, or n by 1, sorry. So this is the same story. You do it time step by time step. So if you want to do predictions, what do you do? Well, we just said it's easy. You just plug in L, lowercase l here, or j. And the variance of a prediction error, this is one place where we should kind of rewind a little bit to last week. I don't know if you recall. We had the generic formulation last week stating that, I don't know if you recall it, the variance of y, I think we just wrote t minus y hat t equals sigma squared, maybe with a hat, maybe not, depends on the situation. Do you know the uncertainty or don't you know the uncertainty? And then 1 plus, how did I write it last week? I think I made a note on that. I had it as t plus l here, t plus l. Then what we did, then you need the corresponding row in the design matrix, x t plus l transpose, so that it becomes a row. And then we have the full design matrix. I don't have a subscript n here because I don't have it on that form. I have it on, last week we did it on this formulation. It's the same story. We need that inverse. And then we have x t plus l. And maybe this is one of the cases where it's good to do one thing. I usually just skip, but just to underline, this is a vector, that's a vector, those two are matrices. I don't know if you know this notation, but this is one place where it really helps intuition to know, that's why. Dimension and orders, everything fits. And if you do this and transform to the current model structure here, well, basically what you get to is that what you have here is x transpose x inverse. Well, that's the f that we just defined here. So that's the Fn, because we have n observations so far. And then the row in the design matrix is lowercase f transpose L shifts, L steps forward or backwards in time, whatever you want to predict. And likewise at the end here. So the reason why here, when you multiply something on something that is uncertain up here, that the transpose is before what you multiply on, and it's not transposed after the fact, is because it was transposed already up here. Maybe that was disturbing more than it was helping. But usually when you multiply something, then you want the transpose to be on the back side of things. The prediction interval is totally parallel to what we did last week, so I won't spend much time on that. Basically, you just have to find the variance for the particular prediction horizon, take the square root, just get the standard deviation of that. Then you find the appropriate quantile in a t-distribution, and you take your estimated value plus minus that, and you're done. And well, since the variance expression is not too long, we can plug it in. That's basically all there is to it there. There is one thing we'll get back to in detail. That's the estimate of sigma. For now, it's trivial. You do it the same way as last week. It's just the inner product of the errors divided by the number of observations minus the number of parameters, which is the dimension of theta. So pretty much everything is the same, except that we have this Fn in here and use that. So why do you actually want to, why do I want to spend so much time on just restating everything from last week, except for repetition? That comes here. As said, we want to do this repeatedly. Now, when you get an extra observation, what happens to this? You have to recalculate, right? In order to get the next estimate at time n plus 1, you have to do everything all over again, basically. Now, when n becomes large, this matrix here involves a lot of operations. Say, if you're up at 1 million, in order to do this, then you do 4 million multiplications and additions just to create this. So that's 8 million floating integer operations. Then you need to invert it. The good thing is that they're all integers, so it's efficient calculation-wise. Then you need to invert it, and then you have to do a little bit more. But that's the hard part of it. Likewise for h, where you need to do this inner product. It's a lot of calculations. What we want to get to is what later on will be introduced as filtering. Because what you do is that you have all the information that you need is essentially in those two estimates up here. So you have a 2 by 2 matrix and a 2 by 1 matrix that contain all the information you need. So you don't, because, well, it's kind of stupid to redo all these calculations, because most of what you're doing is the same as what you did the step before. So what is it that you add when you go one step forward and you look at this? The last element here is minus n minus 1. And down here, it's n minus 1 square. I won't write it all the other places. There's no space. So when I go one step further, what happens to Fn plus 1? What do I need to add? Can you see that? Anyone? What do I need to add to this when I go one step further forward in time? So this here is what I get out down here. This is Fn. What do I need to add to get to Fn plus 1? Let me write it like this. What do I need to add? Yes?
Like a 1
Yes?
and a 0, the left bottom.
Not a 0.
A -1.
This is the tricky part. No, I understand what you think of is that I just have to do this first row here. But the trick is, yes, but I already had this. What I actually need is to have what is the... I get one more older observation involved. Remember that we shifted our time. So when we go one step forward in time, what we do is to say now this is 0. This becomes -1. This becomes... I should remove the 0 here. This here becomes -n minus 1. And this becomes -n. So what do I have to add? The 1 up here is correct because we always have a 1 there. What comes out there? Or there? Sorry? Exactly, there's a -n there. And it's symmetric, so I can do this immediately. And what is down there? N square. So all I have to do to update Fn to n plus 1 is to calculate those 4 numbers and add them to what I had previously. Do we all agree that I just saved a few million operations? You can say, well, computers nowadays, it maybe doesn't matter so much unless the time is very, very short that you have to do the operations. But there's one more thing to it. When n is increasing in the traditional way, what happens? The calculation time is just increasing linearly. But in this way, the calculation time is always the same. And it's bound to be shorter and less. We can do the same. So that is what is written here. Fn plus 1 is the previous Fn plus F as a column times F transpose of -n. That is exactly what we have down here, right? H is a little bit more mind-boggling. I'll give you that. So how do you get, you can say the last bit, the estimate is of course just doing the same thing. But to invert a 2 by 2 matrix, that's not a lot of operations. And to multiply that on a 2 by 1 vector, we can all do that, right? Even by hand if we ask to. Otherwise we wouldn't. So what do we have to do here? Let's first, I should have done that. Go back and look at the definition of H here. Hn is defined as the sum of j equals 0 to n minus 1 of f of minus j on y n minus j. So how do we move forward from here? Let's just go back to here. n plus 1 well, we could write the whole thing from up there again, and then we just have to figure out how do we get to have hn as part of that up there. So that's how we want to get to it. So we'll just write the full sum here. J equals 0 to n. Now it becomes an n up there, not an n minus 1, because we have n plus 1 down here. And then the j is here still the same. F of minus j y n plus 1, because that's the n we use right now, minus j. That is too short. So first of all, we know that everything here that is related to the time where j is 0, that's the new element we plug in, right? So I will start by saying we have a sum here. If we say j equals 1, true n of f minus j y n plus 1 minus j. I'm squeezing space a little bit too much here. I won't be needing this again. And then I have a plus, and then I left out the first element, that is f of 0. F of 0 on y n plus 1. So that was the last term we have. Now we just have to look at this and say, how does this relate to hn? First of all, the sum has as many elements. The only thing that is different is that time is shifted one step. So j is just shifted one step. So j is always one higher here than there. So what do I have to do? When j is higher here, it means that we are further backwards in time. So what I have to do is I have to shift time, right? So if I in here say, well, what I want to have the sum from 0 to n minus 1. That's what I want to do. So if I want to go backwards and forward, that's what we agreed that the L can do. What I want to do is I want to shift my previous one step backwards in time. So I want to step my previous estimator hn backwards in time to get this, because the y's out here now have a different time index. And then plus f of 0 y n plus 1. So that's the update for h. Again, the inverse of L, that's something you calculate once. So it's a 2 by 2 matrix that you multiply on a column vector with 2 elements. And out here it's a 2 by 2 matrix that you multiply with a number. So rather than having to do the inner product of all the n plus 1 elements that you would have to do otherwise, you're down to doing something that only goes with the dimension of the system, not with the number of observations. I think now it's time to a break. Start 5 minutes past.